I won't need that. I won't need that. All right, we're going to do this in a half an hour. I have spent this year really focused on trying to understand how the garbage collector works. And I'm not going to get into implementation details because I don't have a PhD in any of that. But what I want to show you is how brilliant our garbage collector actually is and how it really gets out of your way quite a bit. And if you're just a little bit mechanically sympathetic with it, it could really get out of your way. I'm going to use some code that I've done other talks on. So if you've seen me give talks around the trace tooling and stuff, you'll see some of the same code, but it's going to be a little bit of a kind of different view of how to use the tracing tool. So we'll do a little live coding. I'll show you how the tracing tool works. You'll see how easy it is to bring that up, and we'll just kind of talk about the garbage collector and some concurrency at the same time. So let's take a look at the initial code here that we're going to be using. Now, the idea of this program is to write a function that can identify the frequency of a particular topic in a set of newsfeed documents, RSS documents. So you can see this function right here. It takes a topic. It takes an unknown number of documents. Right now we're going to play with 4,000 of them, but you got to remember that maybe they want to put 1 million documents through this. So we're going to have to think about that before we're done. And ideally, this is the sequential version of the algorithm. It's really important. I think it's important that you write a sequential version of your algorithms first, because just solving the problem is hard enough. And you start jumping into concurrency issues on top of the problem, it's too much. And nice to have a benchmark with that sequential version to start. So here's our sequential version, right? We've got a found counter there in 55. We're going to range over all the documents on line 57. And then there's basically 4 steps. We're going to open that file. We're going to read the whole thing into memory. It's an XML document. We don't have much of a choice. Then we're going to marshal that into some Go types right there, line 73. And then we're just going to iterate over the news items and descriptions and titles. And every time we find something, what do you want me to do with this? And every time we find something, then what we're going to do is just add to that counter. All right, so not very complex, no big deal. Let's go ahead and we're just going to build this version of the program right now using basically these 4,000 documents that we've made up. The term's going to be present. And one other thing I'm going to do on line 40 and 41 is I'm going to start a trace. So we had a couple talks. Roberto was talking a little about tracing. We're going to see a bit of the tracing tool right now. So we'll start a trace. We'll take a look at what's going on. Ideally, I want to just focus on garbage collection right now, but we can see some other things as well. All right, so I'm going to save this. I'm going to build it. Oh, is that big enough for everybody there? Yeah, it's not bad. All right, I'm going to build it. And then what I'm going to use the time program just so we can get a general sense of how long it's running. And I'm going to write out that trace through the standard out to a t.out file. So there we go. We just finished. And you can see it took about 2.5 seconds, 2.5 seconds to run those 4,000 files. We found that term 28,000 times. But the 2.5 is the interesting number right now. And I've got a t.out file. And so now what we can do is run that trace tool. So go tool trace. T.out, just feed that to the tracing tool, and we get into our browser here. As Roberto said, this tool that we're going to be seeing was really written by the Chrome team. They've retrofitted it. I mean, think about it. Like the language designers are amazing at compilers and runtimes. But what do you think their UI? Yeah, they probably couldn't write it, right? Yeah. So good thing they leveraged something that was already there. So we're going to come in here and click on this. And what we're going to see is a trace of this sequential version that we just ran. So if you've never seen the tracing tool before, here it is. I'm going to knock it down a little bit. The other problem with this tool is whoever put colors against it, they don't really give presentations. I asked them about that. They told me that there was a style sheet. I said, I'm a back-end developer too. I don't touch style sheets. But we get a general sense of what this trace looks like for this sequential version. I really want to focus on the things that are up top, because this is where things, from a garbage collector perspective, get interesting. So take a look into this area right here. I'm going to open this up just a little bit. We're just going to see the start of the program here. Remember again that this program ran for 2.5 seconds. So if you look right where I've got the cursor, this is that heap profile. And let's just talk a little bit about what this heap profile is showing us. You've got that orange line and you got the green line. So the orange line actually is representing how much memory is currently in use at any given microsecond. We're looking at that. But I want you to notice something. Once that orange line hits the top of that green bar that you see, it kind of drops all the way back down. And if you notice, there's a blue line right in line with that drop as well. So what you're seeing in that green area, that green line, is basically the marker that the garbage collector has set to say once this amount of memory is in use, we're going to start a garbage collection. So that's why you're seeing it get to that number, and boom, it drops, gets to that number, boom, it drops. Now, initially when your program starts, that number is 4 meg. So the first 4 meg that your program allocates, that's going to initiate that initial garbage collection. After that, it's all going to be calculated based on what that program is doing, load, and those types of things. But you can see here that we're pretty steady at that 4 meg mark. Now think about what this program does, right? For every given file, it opens, it reads, it decodes, it searches. I mean, really all of the memory that we're using is pretty transient in this program, right? We're not really holding on to anything. It's 4,000 files worth of memory, but we're not holding on to it. So that's why you're constantly seeing these very large drops. We're almost getting back down to 0 in use on every garbage collection because there isn't much that we really need to maintain. All right, so we see this pattern all the way through. And if you really look at it at a little higher scale here, you really begin to see that, this program running sequentially looks pretty stable in terms of its heap. It's maintaining basically a 4 meg heap per collection. And you could see the cadence of the garbage collector by looking at those blue lines. Look, that's a nice cadence going on. But let's look a little bit more at the garbage collector. One of the cool things that this tool does is it does let you select things. And we can use the selection tool here. So one of the things I can do is go ahead and select every one of these blue lines. And what that's going to do is give me these interesting stats around the garbage collector. So we can see that this program required 232 garbage collections. All right? The first garbage collection started at the 18 millisecond mark. The last one there, 2.5 seconds. You can see that we really only had, out of the 2.5 seconds this program ran, 67 milliseconds, nanoseconds, microseconds, milliseconds, was spent in GC. Think about how insignificant right now the garbage collection was really related to this program. What is that, about 2% or something? Of the total time this program ran, there was some garbage collection. You can see that the average collection was taking 291 microseconds. All right, so this is a pretty good base to start with, all right? We now have the sequential version. We can see the garbage collector really is kind of out of our way. We can see how many times it ran. That's good. So now what would be interesting is 2.5 seconds, that's kind of slow. It would be nice if we could speed this program up. And at the same time when we do that, it would be nice to see the impact that we have on garbage collection compared to also, the amount of time that we save running it. So there's a couple of ways that we can do this. We definitely want to now write a concurrent version of code here. And I don't want to try to find the most optimal concurrent version right now. It would be nice just to come up with a simple version, the simplest way to make this concurrent. And concurrency just means out of order execution. So the idea is I don't care what order these files are processed in, as long as they all get processed, right? So the fastest, and really, I would say the fastest, the simplest way right now, at least for me, would be to use a basic fan-out pattern. What if I just gave a go routine every one of these files, right? I got 4,000 files. I'll create 4,000 go routines. I'll let every go routine process their own individual file. I don't particularly care what order that happens in. And then we should be able to leverage the full suite of my machine. Because one other thing that you're going to see here, if you look at this at a higher scale, is that I'm not really leveraging the 12 hardware threads that I have in this computer. This is an i9. It's 6 core. It's got 12 hardware threads. I can run 12 go routines in parallel. And really, if you look at the pink is really my go routine doing the work. Any lines that you see going on are in line with the garbage collector, leveraging more CPU than my program actually is. So we want to fill this whole graph in. I mean, I want to be using every ounce of hardware thread that I have through this entire running program. So let's do a couple things here. Let's turn this into a concurrent version of code leveraging a fan out. So what are we going to do here? We're going to say, how many go-routines do we need? Well, it's going to be based on what? Number of documents. So length documents, G, that's fine. And we're going to have some sort of guarantee point that everything got done. My favorite way of doing that is with a wait group. So wait groups are really nice. They're going to let us just keep that semaphore count of everything that's going on. And then we could just wait group add G, there we go. And we now have the at least number of go routines we're going to wait for. We'll have to come down here at least and now say, we're going to wait until all of that finishes. So we'll do that wait right there. So we've got a part of this orchestration in place. Now what's the other thing? Well, for every document that we're going to be ranging over on line 62, we really want to throw a go routine at that problem. So we could just go right in here, construct that literal function, get that going in here. We now have a literal function for everything. We could finish that wait group work as well. We could defer that done call right in here. And we could say, okay, now as these go routines finish their work, they'll decrement that count. That will help us on the other side. I do have some issues with return. We can just clean that up maybe here. Just clear these out for now. I'm not too worried about that. I've got some other issues here. I've got now a closure bug. Can't have that. So we're going to have to pass that document through. So every go routine does process their own document. That's not bad. We would potentially think we're done here, but we do have a data race right now on lines 88 and 93. We got a data race there. A clean way of cleaning the data race up would be just to go right and use our atomic instructions, right? We can do that add int 32, address found 1. We can use our atomic instructions here and do that, except now it's complaining because found isn't an int 32, it's just an int. We can do that. That fixes the data race. Now we need to do another conversion here. Now, something Roberto talked about was our cache coherency issues, because now what we're going to have is 12 go routines running on 6 cores, and every time they do a plus plus basically on line 90 or 95, we're going to be thrashing that memory again. And one of the answers to that is to really try to leverage local variables, especially in this multi-threaded world. So one of the things we could do is say something like, well, you know what, while this go routine's doing its thing, there's no reason why they have to be doing those atomic calls every single time. We could offload some of those counts internally, right? So we've got some of that atomic out. We still got to update the other end at some point. So we can come back in here at least and maybe finish that work here. And we'll have to move this local variable at the top here, leverage some more closures, but this will work out. And at least this will reduce, so we'll get it down from that 28,000 to 4,000, but it will be better. All right, and we now have a concurrent version of this algorithm, all right? We're able to throw 4,000 go routines at the problem. They'll do their local counters. They'll add their final totals back to our found variable, and we'll wait for all this work to report that it's done. So we've got a decent fan out pattern here. Let's do the following. Let's build this, make sure it still builds. Let's run it. Now, we were at 2.5 seconds roughly before. Let's see where we are now. So we just went from 2.5 seconds to 751. That's not bad at all. That's a pretty nice improvement. Now, let's go take a look at the trace here, because this is what is interesting. I want to see what this trace looks like, what's going on with garbage collection here. So we'll load that up. And so I got part of what I wanted here, right? I got a full graph of of leveraging my machine. You can see that there isn't really much gap going on there. Maybe a little at the end as we're finishing. You could see there in the Go routine section, here's those 4,000 Go routines. Look at up here. 4,000 Go routines coming into existence, right? And look how dense this is. What's happening in here is every one of these Go routines is giving an opportunity to run. So right in the beginning, all 4,000 Go routines get a chance to come to life, and they start allocating memory. They start allocating memory pretty heavy. In fact, we're trying to almost open up 4,000 files pretty quickly. Think about the amount of memory that we're going to need on this version of the program if we're going to let 4,000 files instantly start reading all of that data. So you can see this large garbage collection. And if we open this up, you wouldn't even really see any garbage collection going on here. It's almost not even possible because of all of the work that we're doing here. These are just all of these 4,000 Go routines coming into existence, trying to allocate a little bit of memory at some point, if I can find a good one here, at some point, and then just being put back into these waiting states. Right? You can see the call to malloc GC right there in the second line, and then boom, we're going from running back to waiting. And you're seeing the scheduler try to bring all of this in. And what's happening really is almost no garbage collections going on, but you're seeing all these Go routines come in to their running state and then down into a waiting state, and then they start doing their work again. But I really want you to look at the garbage collection. I want you to look at the blue lines. That's what we're focusing on today. And if I were to select all of the garbage collection that just took place in this program, we'd see some interesting stats. First of all, there's no real cadence to the garbage collector right now, right? We kind of lost that cadence. The garbage collector's trying to figure out these collections based on the massive amount of memory that we're asking for up front, and then as we process these files. But if you notice that this version of the program, even though we've thrown 4,000 Go routines at it, there's only 23 garbage collections that took place, right? 23, but was a total of 153 milliseconds of time across that 751. So this is almost like 30% or something, right? We did the math real quick in our head. So now at this point, we're looking at the garbage collector, eating up about 30% of that total amount of time that we spent trying to solve the problem. But it's still much faster than our sequential version, right? With the average collection of the 23 taking that 6 milliseconds. Okay, so this is interesting, right? We've got a program that's heavy allocating, really upfront. Garbage collectors trying to figure out the right pace here, and it figures out that it's able to do it with just 23 collections, minimizing that down to about 30%. All right, but this version of the algorithm kind of scares me a little bit because I'm really putting some massive load on the runtime, on the scheduler, on the heap. And again, I know it's 4,000 files right now, but what if I end up having 1 million files? I'm afraid to throw 1 million Go routines. Maybe 50,000 Go routines. So we got to find a way. We've got to find a way to figure out how to process the same 4,000 documents, but to keep that small heap, to get that cadence back, okay, and maybe squeeze a little bit more performance just by being sympathetic with the collector. So one thing what we could do here is, since I can run 12 Go routines in parallel, maybe what I want to do is only use 12 Go routines at all. Why do I need 4,000? If I can just use 12 Go routines, then I only need the amount of memory required for 12 Go routines. We could keep that memory footprint fairly static. Maybe we'll get some better sympathies and we'll get a little bit better performance. So let's go back and let's do that. So what we want to do is say, look, I don't care how many documents there are. What we're going to do is just leverage runtime.num CPU. So that's going to be the number of Go routines we're going to use. In my case, that's going to be 12. All of our wait group work is pretty much in shape, but in this case, since it's not going to be based on the number of documents, what we're going to have to do now is create a loop here that's based on G. All right, no problem, we can do that. We can't be passing this in anymore because there's going to have to be another way to feed these Go routines these documents. And really a good way to do that for this program right now is to use that channel. So let's come in, and we'll use a channel, a buffer channel of G. I don't need to put more than G documents in there. Again, I'm trying to keep my memory footprint low here. So we could just always make sure that we got these documents ready to go across these 12 Go routines. And now that we got a channel, what that means is we can come in here and say, okay, every one of you Go routines here, what you're going to do is range over this channel. You're going to feed. Again, this is a concurrent algorithm. I don't care what order. I don't care what order things get processed in. As long as they get processed, I don't care what Go routine done. I don't care what file. So now we can be able to get these documents that I want processed. We still have to feed the channel. So what we can do down here in the end is come back here, and what we could do is load these documents into the channel. Again, we're only going to be putting 12 at a time, so that's going to take a little bit of time, but that little latency that you might think exists there, that latency isn't bothering us at all. Okay, there's other things that we're doing. But once this is all done, once we load the last document into that buffer channel, we'll close it right here, and then we'll wait. And that's a way of signaling all of those Go routines, hey, there's no more work to do after this one. So if you recognize that there's no more work, just shut down, shut down, shut down, shut down, shut down. So with a few quick changes here in a channel, we now have a concurrent algorithm that's going to hopefully leverage our, be a little more sympathetic with our machine, our scheduler, our runtime, all of that. So let's see where we're at right now. I'm going to build this again. We're going to run it again. So we're at 751. Wow, looks like I got a little slower on that one. Interesting. All right, let's take a look at the graph for this program here. And now remember, I'm running this on my machine. If you were to run this on your machine, depending on your hardware, number of hardware threads you can run, all of that, things are going to look a little different. But I do want you to see what's this. I'm going to bring all of these in for a second. Actually, let's highlight this for a second. One thing you should notice is this graph looks very similar, again, to our sequential version, isn't it? We've got that big, thick green line again. We're maintaining that static or that really constant heap size. So there's stability going on there again. You could see that we've got a cadence, again, on the garbage collections. Obviously, they're larger, but remember, we're processing 12 files at a time, not just one. So that seems reasonable to me. And if we look at the numbers here, for the number of collections. We look at the numbers. Let's shrink this in here a little bit. And we select all of these. Let's see what we get. So we're now running, we ran 458 collections, all right? And we went from, we're at 175 milliseconds. What were we here? We're 153 milliseconds. So we ran a little bit more GC here, right? But if you really think about it, I mean, relatively fairly close. And this is really the message that I want to share with you. Look at what the garbage collector was able to do with both of these workloads. Remember, the same number of files are being processed. So at the end of the day, it's really the same amount of memory that's being allocated, right? So there's a constant there. But in one case, we asked the program to just almost load everything up at once. Just go crazy. I don't care. Just load up as much as you can. The garbage collector saw that, found a cadence, found a cadence to deal with that cost us a certain amount of time, right? That was that 153. Then we said, you know what, let's stabilize that memory. It's the same amount of memory again. It's just we're not allocating it all at once. We're going to allocate it over a small amount of time. And if you really think about it, the garbage collection kind of picked up on that as well. And 23 collections over 153 or 458 collections over 175. And for me, it's not the number of collections here, right? Like, if you notice right now, the number of collections wasn't the big deal. It's not the problem. And a lot of people, when they start playing with garbage collection or they start looking at GC traces and they see all these garbage collections taking place, they start to freak out. Oh my God, there's all this garbage collection going on. And you have to slow that down. You have to remember it's not about any individual collection or how many there are. This is a game that's over time. It's the garbage collector saying, look, I'm going to find the pace where I'm going to run so I can get out of your way. But I have to do this. I have to run for you because writing multi-threaded software is so difficult that if I ask you to manage this memory too, it's going to be literally impossible. This is why we have a garbage collector. If we're going to be a language that's going to allow you to leverage the CPU of your machine like this did, well, we can't have that cognitive load. So it's a cost that we want to live with. All right? But you can still see how it basically stayed out of your way. I love the tooling here in Go. It's really interesting. All right? Just got to be careful if you select too much in your browser, because I've had to restart my browser a few times in my life. Anyway, I hope you guys enjoyed this. You saw a little bit of the tooling, played a little bit of concurrency, and you're learning a little bit also on how to kind of look at that garbage collector and see what's going on. And I'm good. I'm not going to delay the conference anymore. So thank you.
Thank you very much. Any questions?
I'll take questions.
No, you have a few minutes for the questions, so we can.
I was just wondering, what happens if you compile it without the GC? How much are you going to gain out of it?
If I tell it to run with it off?
Yes.
Let's run it real quick. We got time, don't we? So let's run it again. I'll just clear this up. All right. So that was what, 780 there? GOGC off. Time trace G dot out. Of course, so let's just export that for now. GOGC. So what was that, 180 milliseconds? Which is kind of in line with kind of what we saw that the garbage collector was in. Remember, we saw about 173 milliseconds before, so you can see that time come off. So that's kind of in line with what we saw, right? But you're not going to do that, right? And if that's the first time you saw that you can do that, wipe it out of your mind.
So thank you, Bill.
All right, perfect.
Thank you.